So we did standardization of a sodium hydroxide solution, and somebody remind me, what is standardization? What does that mean, standardization? Or, okay, let's take a step back. What is a standard? Somebody remind me what a standard is. Regular? Yeah, that's one of the definitions, but this is a very specific definition. Talked about it last week. Does anybody remember? Standards are very important. You can buy them. You know, one standard stored in some vault in France, the kilogram standard. Well, yeah, the representation would be, in this case, the composition. And so when we standardize this, we want to just make sure, we know the composition of this to a high degree of accuracy and precision. And we use the HCl standard solution for this. The HCl standard solution had a accurately determined concentration, accurately and precisely determined concentration. What is it? Yeah, 0.1182. And so to be a standard solution, some work went into determining the composition of this. And the composition of this is 0.1182 moles of HCl, pure HCl, in every liter of this HCl solution. And so what we did in part one was we used the HCl standard solution to standardize the sodium hydroxide solution. And so we'll talk about the calculations today. But we want a good deal of accuracy and precision. So the first thing we got to make sure is that we have good precision. And so somebody tell me the number. Tell me the for trial 1, 2, 3. You pick your 3 best. You throw out all the others. So you pick your 3 closest results. And so let's get the volume of the HCl, volume of the sodium hydroxide. Does somebody have it for me? Just read it off. All right. So what did you get? Okay, the first part, 26, what did you say? 26.75. Okay, what was the volume of the base?
The volume of the base was 25.25.
All right, and then what we did was he took a ratio. He could take the acid over the base ratio or the base over the acid ratio. Just pick one and then just stick with it. And so did you calculate, do you have that calculated? Let's see. We got 26.75 divided by 25.25. 1.0594. All right. What did you get for your next trial? 36.65.
36.65. And for the base, 35.3.
35.30. 36.365. 36.65 divided by 35.3. 1.0382. And then your third trial? 1.70 can't be. You can't read the, Buret can only read to the nearest hundredth. 1.70? Maybe that was the starting Was it 1.70 or?
Oh, okay, so I got 9.7 for trial 3. And I subtracted the initial reading of the acid were read and the final reading.
Okay, and then it came out to 9.7?
Yeah.
Okay, that's a little small. We want a larger volume because when you have when you work with small volumes, then you have something called big relative error. If you work with very small volumes, then you make an error of 1 drop. You know, a 1 drop error in a tiny volume is huge proportion compared to 1 drop error in a big volume. So what we try to do is we try to use as much volume as possible. So if you only use 9.7, then you have a much bigger relative error. If you made a 1 drop error here in 9.7, proportionally, it's a much larger error than a 1 drop error in 36.65. And so in titrations, most people shoot between 35 and 50 milliliters. Between 35 and 50 milliliters, that'll give you less error. That'll give you better results. And so 9.7. 9.7 is a little low, but...
And the base I got 10.
And 10.00? Okay. All right, so we'll take the acid divided by the base. 9.7 divided by 10 is 0.9700 sub 0. Okay, now what we're going to do is we're going to pick the biggest, which would be 10.594. And so we'll do the percent difference. The percent difference is the biggest, which was going to be 1.0594, minus the smallest, 0.9700, divided by the smallest, 0.9700. And so let's do that. 1.0594 minus 0.97 equals divided by 0.97, and then times 100%. And so the percent difference here comes out to 9.2, say about 9.21%. But what is the max allowed? The max allowed is 0.5, and so this is going to require a fourth.
Yeah.
Oh, you did a fourth? Okay, what did it come out to?
After doing the calculations for the fourth one, I did it was 1.7 for the acid, volume acid, and then 1.7 for
Okay, 1.70 for the acid and 1.704.
Yeah, for the base.
Well, we can't have, it has to be, was it 1.7 or 1.74?
1.7.
1.7? Okay. So 1.7, 1.7? So again, a milliliter is about 20 drops. And so we could do it. A 1 drop error in 1 milliliter is about 0.5% error. A 1 drop error in 40 milliliters is negligible. It's very small. And so that's the reason why. And so if we have 1.70, automatically you're handicapping yourself because you're going to have a huge error, relative error. And so these are too small, volumes are too small. But it could be you're running out. In fact, some people did run out of sodium hydroxide. In the stockroom is it doesn't have much sodium hydroxide, I guess. Well, anyway, let's pick the 3 closest. Well, now what we're going to do is we're going to eliminate this one, number 3, and we pick the 3 closest here. And let's go ahead and do our calculation over again. So it's going to be 1.0, the biggest, 1.0594 of the 3, minus the smallest of the 3, best ones, divided by the smallest times 100. And so it's better, if we pick these three, we end up with a percent difference of 5.94%. So we went from 9% to 6%. So it's better, however, it's not good enough because, you know, we're trying to make a standard. We're trying to standardize this sodium hydroxide. So we're trying to determine this composition to a high degree of precision and accuracy. And so what this requires is, this is going to require a fifth trial. We'll do a fifth trial and then throw out the worst one. You know, pick the three best ones, the three closest, and then repeat the calculation, biggest minus smallest.
I don't know if I did make the calculation wrong, but I didn't do it in decimal. I kept it in, like when I was doing my calculation, I kept it in fraction form. And then I got
Point 0.0382? Okay, tell me what were your fractions that you used?
36.65 over 35.3 minus 9.7 over 10.9.
10.9 or 10.0?
Oh, 10.09.
10.09?
And then, wait. I think this is wrong. Wait, the last one would be 1.7 over 1.7. So the 9.7, like, erase that one.
Okay. You did 1.7 over 1.7?
Yeah. And then divide 1.7.
And divide both by 1.7 over 1.7?
Yeah.
Okay.
And then
Well, 1.7 over 1.7 is 1,
Yeah.
so this is 1. And so that's going to be 3665 over 3530 is 1.038. Is that right? 1.0382? Right?
Yeah.
Okay, yeah, then you're going to get, you got 3.82%, correct?
Yes.
Yeah, there's one problem with this. That's fine, that calculation is correct.
Okay.
But that's only 2 trials. Because you threw out this trial, and you're just using these 2 trials. We need 3 trials that agree within 0.5%. You only have 2 trials that agree within 0.5%. So you still need to do one more here, because this one, it came out even bigger. So you threw out this one and used this one as the biggest, although this is the bigger one. You see? And so, yeah, that's correct. If there was one more trial that fell between these 2, it would have been okay. And so what do you need to do? Well, you need to make sure that you got 3 good trials. Once you have 3 good trials, then what we're going to do is do the calculation. And so one person ended up doing 8 trials. 8 trials. They had a leaky burette, and that was causing them problems. And then one person wasn't able to get any. They had a huge bubble. I looked. They had a huge bubble. This happened last year, and I mentioned it at the beginning, but they still had a huge bubble this year too. And, just thought, didn't see it. So then I decided I'll check everybody's. And when I checked everybody's, there are three people who had big air bubbles still in the burette, this morning. And they weren't able to, and I asked one of them, why weren't you able? It was difficult. They couldn't get rid of it, so they just left it there. But if you just leave it there, it's going to screw up your results. So I can help you. I helped her get rid of that. But, I can help you guys get rid of that air bubble if you're having difficulty getting rid of it. But you better make sure you get rid of it, and you better make sure there are no leaks too. The other common thing that happens is people misread the burette. And so if you're uncertain if you're reading it correctly, either ask me or ask your neighbor to verify the reading. Just make sure it's reading correctly. Because there were people in the morning who were not able to get less than 0.5% precision. Okay. So make sure. Okay, once we get it, then we got 3 trials. So this is the reaction, HCl plus sodium hydroxide yields salt and water. So H2O liquid plus NaCl aqueous. Now, in part 1, we want to determine the concentration of the sodium hydroxide. That is, we want to determine the composition of the sodium hydroxide. The composition is going to be given by the concentration, which is in molarity. Molarity is we want to figure out how many moles of sodium hydroxide there are per liter of sodium hydroxide solution. So the molarity, half of this is going to come from stoichiometry. And so we'll get the moles from stoichiometry. That is, when we have molarity, it makes stoichiometry a lot easier. And so all we're going to do is we're going to go from milliliters of HCl solution to liters of HCl solution. Once we have the liters of HCl solution, then we know the composition of that HCl solution. The composition of that HCl solution was the point, what was it, 0.1182? 0.1182 moles of pure HCl per liter of HCl solution. And so we can go from the liters of the HCl solution, the mixture, into moles of pure HCl. Once we have moles of pure HCl, then we can figure out how many moles of pure sodium hydroxide we have. And so that's going to take us here. And so the final step of this is just to figure out the molarity. We can get the molarity just by dividing it by the liters of sodium hydroxide solution. So we just divide it by the liters of sodium hydroxide solution, and then we get the molarity. The liters of sodium hydroxide solution, well, that just comes from the titration. And so we'll just have the moles of sodium hydroxide from the stoichiometry divided by the liters. So we're going to get the milliliters of sodium hydroxide that we used in trial 1. However many milliliters that is, it should be x.xx milliliters, and then just convert it to liters. A liter is equivalent to 1,000 milliliters. And so that's what we'll do here. So that's this final step in determining the molarity. And so we have all the numbers here. We have the milliliters of HCl and the milliliters of sodium hydroxide, which is going to take us here. All right, we're going to do the calculation for all 3 good runs. And so for run 2 or trial 2 and trial 3, and then once we do the 3 trials, what we'll get is an average. And so we'll just take the 3 and average those to get the molarity, the average molarity of the sodium hydroxide. Once we do that, then we've determined the sodium hydroxide composition to 4 sig figs with good precision and hopefully good accuracy. And so now this has been standardized. All right, once the sodium hydroxide is standardized, then we're going to go to part 2 of this. And in part 2, what we're going to do is we're going to use this sodium hydroxide standard to determine the concentration of an unknown acetic acid. And so in part 2, we're going to determine the composition or the concentration of an unknown acetic acid solution. Acetic acid is vinegar, so oftentimes this would be used to analyze the composition of vinegar solutions. You know, how much vinegar, how much acetic acid is in there. Okay, determine the concentration of an unknown acetic acid solution by titration against the sodium hydroxide standard. now the sodium hydroxide has been standardized, we can call it a standard solution. All right, so we're going to do the same thing here. We need 3 good trials. That agree within 0.5%. And so what we'll do, we're just going to do a simple calculation just to check agreement. We aren't going to do the final calculation. And so that is, we're just going to take the volume of the acid divided by the volume of the base, or it doesn't matter, or the volume of the base divided by the volume of the acid. You know, we just want a ratio. And this ratio should be the same for all 3 trials. But they aren't. You know, there's going to be some slight experimental variation. But we want to make sure that experimental variation is kept to within 0.5%. All right, are there any questions about this? No? And so everybody's going to have their own unknown. So you'll have to get the unknown number. One of the things you have to get in the habit of doing. Actually, there's no spot for the unknown number here. The station number, you have to put your station number there. Part 2. Your station number or drawer number will be your unknown number. And then you'll get approximately 100 milliliters. And so with the stockroom, what happened this morning is they want you to get the burette and the burette clamp first, and then go back a second time with the beaker for your unknown acid. Okay, so first time just grab the burette and the burette clamp. Second time bring a beaker. Okay? Otherwise, that's $400 worth of burette, and so they don't want you to break it by accident. Okay? All right, I'm going to stop here if there are no questions, and we'll just get started.